A projectile is fired vertically upward with a speed of 62 meters per second. In the absence of air resistance, the maximum height of the projectile attains is. So we're looking for delta y, the maximum displacement vertically. They told us the initial velocity is 62 meters per second, and we know that the acceleration comes from gravity in the opposite direction, so it must have the opposite sign. If upwards positive 62 is the initial velocity, then downwards negative 10 is the acceleration. At the highest displacement, the largest displacement, the final velocity is 0, and we're looking for delta y. The formula we would use that has all four of these variables is v squared is equal to v naught squared plus 2a delta y. In order to rearrange this formula to solve for delta y, we're going to subtract v naught squared from each side and then divide by 2a. That gives us v squared minus v naught squared divided by 2a. V is 0, so 0 squared minus v naught squared. So we're going to subtract 62 squared and divide that by 2 times negative 10. So 62 squared, then made negative, divided by negative 20. It's like we get 192.2 meters. The closest viable answer would be C, 200 meters. It's okay if it's not the exact. We're just finding the nearest answer. Have confidence in the work that you do. A ball has been thrown vertically upward. The graph shows the ball's position as a function of time. Which of the following statements best describes the motion of the ball? The velocity of the ball is the same at points A, B, C, D, and E. We know that's not correct because of acceleration of gravity. The acceleration is 9.8 everywhere but C. No, gravity still works at point C, so that's not true. The acceleration is negative 9.8 everywhere but C? No. The ball is the same distance above the ground at points B and D. Obviously not. We can see that from the picture. The velocity of the ball changes continuously during its flight. Absolutely. There is an acceleration from gravity, so the velocity is continually changing. A brick is dropped. Dropped means v naught is equal to 0. That's the initial velocity. It's dropped from rest, so they're telling us in two ways that it's v naught is 0. The displacement is 5 meters. How long does it take? So we're looking for time for the brick to reach the ground. So we need to know three things. The height is 5 meters, acceleration is 10 meters per second square, initial velocity is 0. If you want the acceleration to be negative 10, you need to make the displacement negative 5 because they're both in the downward direction. They have the same direction, they have the same sign. We know that delta y is equal to v naught t plus 1/2 at squared. We're solving for time, and v naught is 0, so v naught t is going to be 0. It's gone. So we want to rearrange this to solve for time. We're going to multiply both sides by 2 to get rid of the 1/2. We'd have 2 delta y is equal to at squared. And if we're solving for t, we would just divide both sides by a and then square root it. We would have divide both sides by a, we'd have 2 delta y over a is equal to t squared, and then we square root both sides to make it equal to t. Then we just plug in our numbers. We'd have the square root of 2 times 5, which is 10, divided by a, which is 10. So the square root of 10 over 10, which is square root of 1, which is 1. Best answer is B, 1 second. A car starting from rest, so v naught is 0, accelerates in a straight line path at a constant rate of 2.5 meters per second square. So the acceleration is 2.5 meters per second square. How far? We're looking for delta x. Will the car travel in 12 seconds? So v naught is 0, acceleration is 2.5 meters per second square. Delta x is what we're looking for, and time is 12 seconds. The formula that we're going to use that has all of those variables is delta x is equal to v naught t plus 1/2 at squared. Just like the previous question, but we used y in the previous question, delta y, because it was moving vertically. This is moving horizontally, so we'll use delta x. V naught is 0, so v naught t would be 0. Delta x is equal to 1/2 at squared. If we start plugging in, because we're solving for delta x, we'd have 1/2 times 2.5 times 12 squared. So half of 2.5 is 1 1/4. 1 1/4 times 144, because 12 squared is 144. We get 180 meters. A is the best possible answer. Number 5, a car starts from rest and accelerates at a constant rate in a straight line. In the first second, the car covers a distance of 2 meters. How fast will the car be moving at the end of the second second? We can use the first second in order to determine what's going on with the system because we have a little bit more information for that first second of travel. So V naught is 0, and it covers, in 1 second, it covers a displacement of 2 meters. Now what we do have in common between the 2 seconds of travel is the acceleration. So I'm going to put that A back in there, and we're going to be looking for acceleration, knowing V naught, knowing time, and knowing delta x. For the second second, or for this, we can say, well, for 2 seconds of travel, V naught is still 0. We don't know the acceleration, time is 2 seconds, and we want to know what the final velocity is, right? So if we were to get the acceleration for the first second and then apply it for the entire trip, we could figure out how fast they're going at the 2 second mark. Delta x is equal to V naught t plus 1/2 at squared. V naught t is 0 because V naught is 0. So delta x is equal to 1/2 at squared. Multiply both sides by 2. And you get 2 delta x is equal to at squared. Divide both sides by t squared, and that solves for a. So 2 times 2 meters divided by 1 squared. That should give us 4 meters per second square for our acceleration. If our acceleration is 4, we can put that into the second column of known. And it looks like, I think we can use VOTAT because we have the initial velocity, we're looking for the final velocity, we have the acceleration, we have the time. So V is equal to V naught plus A times T. We're looking for V, so no rearrangement. We've got 0 plus 4 times 2. So the final velocity after 2 seconds is 8 meters per second. A ball is dropped from rest from a window. Everything dropped is dropped from rest, so you know V naught is always 0. At the same instant, ball B is thrown downward, and ball C is thrown upward from the same window. So okay, so maybe I can do this a little differently. Let's draw a window. We're going to drop one ball, so we'll just do one arrow down. That's ball A. Ball B is being thrown down, so let's give it a little bit more force, a couple extra arrows down. And then ball C is thrown upward, so let's give it some up force arrows. Nothing complicated, just to show us what's going on. Which statement concerning the ball is necessary true if air resistance is neglected? All right, A, at some point after it is thrown, the acceleration of ball C is 0. No, ball C is always accelerating, has gravity acting on it. All 3 balls strike the ground at the same time. No, the one thrown down will get there before the one thrown up. All 3 balls have the same velocity at any instant. No, the one dropped will have a different velocity than the one thrown at any instant. All 3 balls have the same acceleration at any instant. Well, yeah, same acceleration. It's called gravity. All 3 balls reach the ground with the same velocity. No, the one thrown down will get there a lot faster velocity than the one simply dropped. So D is our best answer. Use the following to answer questions 7, 8, and 9. A tennis ball is shot vertically upward in an evacuated chamber, no air. That's just extra info. With an initial speed of 20 meters per second at time equals 0. So don't get hung up on time equals 0. Okay, time equals 0 just simply means that at the starting point is thrown upwards. So our V naught is 20 meters per second. We know that acceleration is 10 downwards. It's in the opposite direction, so it's going to have the opposite sign. So how high does the ball rise? We're looking for delta y, and at the highest point that it rises, final velocity is equal to 0. If we're going to solve for delta y having V naught, V, and A, our best equation is V squared is equal to V naught squared plus 2A delta y. We're solving for delta y, so we're going to subtract V naught to the other side, or V naught squared to the other side. And then once we do that, we can divide both sides by 2a. By dividing by 2a, I get delta y on one side, and I get v squared minus v naught squared divided by 2a on the other. We can plug in our numbers. V squared is 0, 0 squared, and then we're going to subtract 20 squared, and then we're going to divide by 2 times negative 10, negative 20. So if I do my math correctly, it looks like it should be 20 meters. Yeah, it is. So my best option there is B, 20.4 meters. Approximately how long does it take for the tennis ball to reach its maximum height? Well, we're looking for time. We know that final velocity is 0. We know initial velocity is 20, and we know acceleration is negative 10. I don't want to use that delta y value from the previous answer, because what if I was wrong? We're not introducing trash answers into new computations unless we have to. So we're just going to use VOTAT. It's preferred anyway by me. It has a fun name, and it's no fractions and no squaring. So we've got v is equal to v naught plus a times t. Subtract v naught from both sides, and then divide by a on both sides. You get v minus v naught over a. V is 0 minus 20 over negative 10. And that's equal to time. Looks like time should be 2 seconds. B is our best answer. Last question using this scenario is going to be number 9. Determine the velocity of the ball at time equals 3 seconds. So we're looking for final velocity, and we've got time equals 3 seconds. Initial velocity is still 20 meters per second up. Acceleration negative 10 meters per second squared down. So VOTAT is our equation. We're looking for final velocity. It's already set up for that, so we can just say 20 plus negative 10 times 3. 20 minus 30 should be negative 10. So the ball is coming back down at 10 meters per second. So our best answer is going to be A. Because it's negative, we're looking for downward, and 9.4 is our best answer if we're looking for 10. Fresh question. A projectile is fired with an initial speed of 1,000 meters per second at a 37-degree angle above horizontal. So we're going to draw that picture out. If air resistance is neglected, horizontal component of projectile's velocity after 20 seconds is approximately. Well, they're wanting Vx. And the good thing about Vx is there's no acceleration. So if we determine what Vx is in our little triangle here, our little velocity triangle, that is the velocity at 2 seconds, 20 seconds, 14 seconds. As long as it's still airborne, that's the velocity. Do not let it saying initial velocity or anything else throw you off. Vx is calculated as the hypotenuse cosine angle, 1000 cosine 37. Put that into our calculator in degree mode. Make sure you're in degree mode. I get 798.63. Best possible answer, 800 meters per second. Number 11, which of the following statements is not true of a projectile moving near the surface of the Earth against negligible air resistance? The horizontal velocity is constant. That's good. The vertical acceleration is constant. Yep, gravity. The horizontal displacement is directly proportional to the time in flight. Yes, the longer it flies, the further it goes. The vertical velocity at any given time is independent of the angle of projection. Independent? The steeper the angle, the more the overall velocity is contributed to the vertical, right? If I go straight up, all the velocity goes vertical. If I go horizontal, none of it goes vertical as far as initially. And let's look at E real quick. The horizontal acceleration is constant. Yes, it is 0. It is a constant 0. So D is the one that is not correct. D. Number 12, a golfer drives her ball from the tee down the fairway in a high arcing shot when the ball is at the highest point of its flight. And it looks like I'm just justifying number 11 a little bit more. Saying V naught is the hypotenuse sine angle, so of course the angle is important. Okay, going back to the golfer. When the ball is at the highest point of its flight, its velocity and acceleration are both 0. Nope, gravity does not go to 0. All right, let's get the cute little picture. Ball's on a tee, goes into flight. Yes, we all love my artwork. And we're looking at there at the top. So the acceleration is not 0, so A is trash. The velocity is 0, but the acceleration is non-zero. Well, the overall velocity is not 0. because it still has horizontal motion. The velocity is non-zero, but the acceleration is zero. The acceleration is not zero. Gravity. Its velocity and acceleration are both non-zero, kind of like it. Insufficient information. No, there's no insufficient information. There's still horizontal velocity, so it's still moving. I know that vertical velocity goes to zero, but there's still a component of horizontal velocity during its flight, so we cannot say all velocity is zero. Use the following to answer questions 13, 14, 15. The figure represents a parabolic trajectory of a ball going from A to E. In each gravity, but without air resistance. In Earth gravity, not each, Earth gravity. What is the direction of the acceleration at point B? Point B is under the influence of gravity. Gravity is straight down. The figure represents blah, blah, blah. What is the direction of the acceleration at point C? Gravity. Gravity is the source of the acceleration, and gravity goes straight down. Please don't miss this question on a test. The figure, okay, what is the speed at point C compared to that at point A? Well, let's go back up to the diagram. Point A, B, C, D, and E all have the same horizontal velocity. Point A has the largest positive vertical velocity. B is going to be a little bit smaller. C has no vertical velocity. D has kind of a medium downward vertical velocity. And then E would have the largest downward vertical velocity. So if we're making comparisons, C has less than A because they both share the exact same horizontal, but A has a bonus of that upward velocity. A cannon is fired from the top of a 75-meter tall tower. If it lands 150 meters away, what is the initial velocity of the cannonball? So what variable is it looking for? Well, if it didn't give us an angle, there must not be one. It's shooting it horizontally. If it's the initial velocity of the cannonball and the cannonball is initially going horizontal, it's looking for Vx. It's looking for Vx. That's the only way we can explain it. It's moving in both horizontal and vertical, so we've got to make an XY table. Delta X is 150. We don't know Vx. That's what we want. We don't know time. Delta Y is 75 meters. V naught is 0 because it wasn't shot up or down. Acceleration is going to be 10. I'm making it positive. If you want it to be negative, go back up to your delta Y and make that negative because they're both downward. And then time. In order to solve for Vx, we need time. So let's use the right side of this table to solve for time, and then we'll throw it over there to the left side. Since we have everything except for final velocity, our delta Y is equal to V naught T plus 1/2 AT squared is going to be our best equation. V naught T is 0 because V naught is 0. And that leaves us with delta Y is equal to 1/2 AT squared. And if we just want to plug in some numbers and save some time, we've got 75 is equal to 1/2 times 10 times T squared. So 75 is equal to 5T squared. Divide both sides by 5 and then square root. That will get you the time. Don't forget you have to square root. That is T squared, and we're looking for T. 15 is T squared, so that means T has to be 3 point something. 3.87 seconds is our time. And for the left side of our table, we know delta X is equal to Vx times T. So delta X divided by T is equal to Vx. So we're going to take our 150, we're going to divide by 3.87, and that will get us the velocity that the cannonball came out of the cannon. In this case, it was all horizontal. Looks like I'm getting 38.76 meters per second. All right, graph shows position versus time squared is shown below. Sketch the graph of position versus time. So they use it T squared because T squared allows you to linearize the graph, where it was drawn kind of parabolic. It was the right side of a smile, even if you want to say it that way. The next question wants us to create to calculate the slope, and it looks like it intersects. And it's the slope of the straight line. It's not the slope of the curved line. You can't get a slope of a curved line, not very easily. It looks like it goes through the origin, and then for me, I can see it goes through 4, 7. So the change in y over the change in x, I would have 7 minus 0 over 4 minus 0, because I rise over run. And when I do 7 divided by 4, I get 1.75. So my slope is 1.75 meters per second square. Those are the units from the table. What kinematic equation does the line describe? Well, I've got x versus t squared for my graph. So what equation has an x on the left, or a y, doesn't matter, and on the right it has a t squared? Well, delta x is equal to v naught t plus 1/2 at squared. And if you think about it, y equals mx plus b. Whatever is attached to the variable from your x-axis, in this case t squared, is your slope. So my slope is 1/2 a from right above. And if my slope is 1/2 of a, all of a would be 2 slopes. So it'd be 2 times 1.75, and 2 times 1.75 should get me 3.5 meters per second square. Find the slope of this line. So I see it's at 0.4, and then I've got another one at 4.14. So change in y over the change in x. Should have what? 14 minus 4 over 4 minus 0. So that gets me 10 over 4. 10 over 4. 10 divided by 4. 2.5. And this would be meters per second square, because I'm looking at the units. Rise over run. What is the kinematics equation that best describes the line? Well, on the left side I've got velocity square. On the right, on the horizontal axis, I have meters. So what equation do I have? V squared on the left and meters on the right. V squared is equal to V naught squared plus 2a delta x. So according to the graph, what is the acceleration of the cart? Well, if we're using y equals mx plus b, the m is attached to the horizontal axis variable. So here 2a would be my slope. My slope is 2a, 2 times the actual acceleration. My slope is 2a, so half of the slope would give me 1a. So my acceleration is going to be 1/2 of the slope of my line. Half of 2.5 is 1.25 meters per second square. According to the graph, what is the initial velocity of the cart? The initial velocity of the cart should be 2, right? Because it says v squared at time point 0. If it crosses the y-axis at 4, then the initial velocity should be 2. Not the initial velocity squared, right? Okay, last page. So plot a graph of position versus time for each of the 2 carts in the space below. Fill in the scale for the position axis, the result values. Okay, so for cart A, it looks like the velocity is a constant 20. So that means my slope needs to be a constant 20, because the slope of my position line gives me my velocity, and it's going to be a constant 20. So I'm going to draw a line right through here. It has a cute little tool where it'll just snap it straight for me. And bam, look at that. Now for car B, I've got a changing velocity. There is an acceleration. The velocity graph has a positive slope, so I know I've got a positive acceleration. It needs to look like one side of a smile, and this time it's going to be the right side of a smile. And I'm just going to have to kind of choose a couple of spots strategically in order to create slopes that coincide with the current velocity at any kind of moment in time. It is a little tricky. I don't want you to overanalyze this one. Just getting an idea of what to expect, that sort of thing. So here I'm going to say, okay, well at the 4-second mark, I've got 40 meters per second. I'm sorry, I've gone 40 meters at 4 seconds. And at the 8-second mark, let's see if I kind of do a little bit of math, maybe 200 meters. Because if I do a straight line from 4 seconds to 8 seconds, and then use that change in y and change in x, that will give me the right velocity at 8 seconds. Whether it works out or not, it's going to be fine. Again, don't overanalyze. If we both have the right side of a smile, we're chill. Determine the time at which car A and car B have the same velocity. Justify your answer. And it's at the time point 4 seconds. The velocity versus time graph shows car A and car B at the exact same velocity value. So we're going to get that directly from the graph above. So at time point 4 seconds, the velocity versus time graph shows both cars to have a velocity of 20 meters per second. How far has car A traveled when both cars have the same velocity? So we want to know how far has car A traveled. Here we can look at the area under the curve, but we're not really doing motion graphs right now. We're doing kinematics. So let's see if we can do it the kinematics way to make sure we're exercising those tools, those skills. Well, we know that we have a constant velocity, so there's no acceleration. So the velocity is 20, time is 4, and displacement is velocity times time. And if you did the area under the curve, you'd be doing velocity times time, the base times the height. And we get 80 meters. Let's see. And I'm just going to write could also use area under the curve. It is legitimate to use it, but again, we should be practicing the things within the unit so that way we're preparing ourselves for the assessment. How far has car B traveled when both cars have the same velocity? Well, car B had an initial velocity of 0. It had a final velocity in this time period of 20 meters per second. The time we determined was at the 4-second mark, and we're looking for delta x. Provided this information, the best equation for us would probably be v squared is equal to v naught squared plus 2a. Well, in order to do that, we'll need to know the acceleration. So where are we getting the acceleration from? That's right. If we look at the slope of the initial graph from the velocity graph, we can get the acceleration. So the acceleration is known to us. So we can use one of two equations. Now we have so many known variables, we can use delta x as v naught t plus 1/2 at squared. And without acceleration, we could use delta x is equal to 1/2 v plus v naught times time. V naught's 0, so we can get rid of that portion on the left, and we get delta x is 1/2 times 5 times 16. On the right, we have delta x is equal to 1/2 v plus v naught, 20, times 4. Delta x is 40. Yeah, I do see that error that I made, but I think I didn't carry it into my math. So I put the 1/2 and then I cut the acceleration in half, but I didn't carry that in my calculation. So 40 is still the correct answer. I'll fix that on the key. Where I'm talking about in that first equation where I put 0.5 times 2.5. I applied the half to the 5, and then I kept it in there, just in the written. And I could have also used the area under the curve. Last question, determine the time at which car B passes car A. Justify your answer. So when they pass is going to be the moment after they have the same displacement. So you've got one car catching up to the other. At the moment the displacements are the same, that's the moment they're going to be passing each other. So they're going to have the same time, they're going to have the same displacement, different velocities. So if we say the displacement for car A has to be equal to the displacement of car B, for car A we know the initial velocity is 20, the acceleration is 0, final velocity is 20. Time is what we don't know because that's what we're looking for, the when. For car B, we know that the initial velocity is 0. The acceleration is 5 meters per second squared. Time, we don't know, that's what we're looking for. And the time for each of them is the same. On the left side, we can say delta x is equal to 1/2 v plus v naught times t. On the right, we can say delta x is equal to v naught t plus 1/2 at squared. Now we can set those two delta x is equal to each other because we're looking for when their displacements are the same. So we can have, for car A, the 1/2 v plus v naught times t is equal to, for the car B, v naught t plus 1/2 at squared. We're not going to rearrange anything. We're solving for time, but we can plug in our numbers. On the left side, we'd have 1/2 40 times t. And on the right side, v naught t goes away, and we'd have 1/2 times 5 times t squared. On the left, you have 20t is equal to, on the right, 2.5 t squared. Divide both sides by t. T goes away on the left, square goes around on the right. Now we're just going to divide both sides by 2.5 to solve for t. 20 divided by 2.5 is 8. The time when they meet up and one car passes the other is 8 seconds.